All right, today's lesson for our unit, Light and Optical Systems, is on topic 2, which is on reflection, but it will be broken up into 2 lessons. All right, so reflection, this is the process in which light, it will strike a surface and then it'll bounce back off that surface. So for example, light reflecting from a mirror allows you to see an image of yourself. When you're reading, this is also reflection from a printed page. All right, so here we have 2 images. We have image A, that's the surface of a paper, and image B, I believe, is like something like a smoother, flat surface, like we could say a mirror. All right, so this one, when we look at image A, the surface of the paper is much more rough. So you can see what's happening with the ray diagrams. They're kind of bouncing off at different angles. But if we have a smooth, flat reflecting surface, you can see that all of these incoming rays and reflecting rays are all kind of angled the same. And we will look at that more as we continue with the lesson. Okay, so there is something called an incident ray. This is the ray that comes from a light source and it's going to strike the surface. And then we have the reflected ray. This is the ray that will bounce off the surface. All right, so to describe the direction of these rays, we're going to create these ray diagrams. So the first thing we're going to do is we draw a line that is perpendicular to the reflecting surface. So anytime we talk about making a perpendicular line, it's going to make a 90-degree angle. So this line that is perpendicular to the reflecting surface, it's going to be exactly at the point where the incident ray strikes the surface, and that line we're going to call the normal line. So if we look at our image here, this is the normal line right here, labeled as normal. It is making a 90-degree angle here with the reflecting surface. So 90-degree angle. And that line is called the normal line. Next, we have an incident ray. That incident ray is going to make an angle with the normal line, and that is called the angle of incidence. Okay, and it's shown as a lowercase I. So again, this is the angle made between the incident ray and the normal line. So let's just take a look at that image here. Right, this is the incident ray. So it's coming in. You can see the arrow is pointed towards the reflecting surface. So it's coming in and it's going to hit right there. And this angle shown with the lower case I, that is the angle of incidence. So again, it's made with the incident ray and the normal. And next we have the reflected ray, and the reflected ray is going to make an angle as well. The angle between the normal line and the reflected ray, that is called the angle of reflection, and it is shown by lowercase r. So let's take a look at our image here. So here is our reflected ray. You can see our arrow pointing now away from the reflected surface, and then we have lowercase r here showing the angle of reflection. Okay, and again, it's made between the reflected ray and the normal. Okay, so the normal, again, it's a reference line that is drawn perpendicular to the reflecting surface to make that 90-degree angle. And it's drawn at the point where an incident ray strikes a reflecting surface. So right there. All right, then we have the angle of incidence shown here with the lowercase I. It's the angle made between the normal and the incident ray. And then we have the reflected, the angle of reflection shown by the lowercase r, and that's the angle that's made between the normal and the reflected ray. So here we just have an image showing the surface of a lake and how it can be so smooth that it provides a near perfect mirror image of the scenery around it. All right, so kind of here we can see where the lake is. All right, so just a nice image. So next, we're going to talk about forming an image, and we're going to start by talking about the law of reflection. So the law of reflection states that the angle of reflection equals the angle of incidence. So for example, if the angle of incidence is 60 degrees, then the angle of reflection will also be 60 degrees. So if I just go back to this image here, so if we say here that this angle here is 60 degrees, this angle here, the angle of incidence, then this here will also be 60 degrees. All right, and just keep in mind that here the normal, this angle here that's made is a 90-degree angle, shown by that little box. So again, the law of reflection, the angle of reflection equals the angle of incidence. The incident ray, the normal line, and the reflected ray line, they all lie in the same plane, meaning the imaginary flat surface, they are all on that same plane. Okay, so in this example, we are looking at an incident ray coming in. We have a reflecting surface here, something like a mirror. So we have the incident ray coming in, it's hitting the reflecting surface here. So this is the point where we would make that normal line. So this line here would be the normal. So I'm just going to label that. That line there is the normal. Okay, and then we have the reflected ray coming off. Again, the arrows are pointing, if it's an incident ray, it's pointing towards the reflecting surface, and then the reflected ray, the arrow is pointing away from the reflecting surface. All right, so the angles that are made here, here is the angle of incidence, and here is the angle of reflection. All right, and because of our law of reflection, which states that the angle of reflection is always equal to the angle of incidence. So the next part here is how do reflected rays form an image that you can see in a mirror? So it's a light. Light is shining. So in this example, we have light shining on the blueberry. And this light reflects off all the points on the blueberry in all directions. All right. So in this figure, we're only seeing the rays coming from one point being shown. So just from this point right here. But keep in mind that the light reflects off all points on the blueberry in all directions. So all of the rays from the blueberry that strike the mirror will be reflecting. So we can see as they strike the mirror, they are reflecting or bouncing off. So the rays that reach your eye, they are appearing to be coming from a point behind the mirror. But the brain, it knows that the light travels in straight lines, and the brain is able to interpret the pattern of light that reaches your eye as an image of a blueberry behind the mirror. So that's how the brain is interpreting or forming that image that you see in a mirror. So let's take a look here at another one, forming an image. So we have a bird here. This is the image of a bird. And then this here is the plane mirror. All right, so rays are shown coming from 3 different points on the bird. Shown in the 3 different colors. We have like the orange, purple, and the green. So these rays, they reflect off the mirror and back to the bird's eye. Okay, the points, they appear to be coming from behind the mirror. All right, so such as behind the mirror shown here, that's the image of the bird. So each point appears to be coming from a point that is as far behind the mirror as the real point is in front of the mirror. So the 3 points, they're exactly the same distance apart in the image as they are on the bird. And these observations, they explain why an image in a mirror, plane or flat mirrors, is the same size as the object and appears to be the same distance from the mirror as the object. All right, so let's pause here and take a look at a couple videos. Okay, so the next part of this topic on reflection is curved mirrors. So the first type of curved mirror we're going to talk about is the convex mirrors. These are the mirrors that bulge outwards. All right, so these types of mirrors are going to form images that appear much smaller and farther away than the original object. All right, but it can reflect light from a large area. So they are often used as security mirrors in stores. You may have seen them up at the top, like corners of stores. So basically, one clerk can see everyone in a small store in the mirror. Also used on the passenger side of cars and trucks, the driver is able to see many of the vehicles that are behind the car. All right, so here, useful as security devices in stores. Here, as a side mirror. Next, we are looking at concave mirrors. These are mirrors that are caved in like a bowl. So they are very good at collecting light and bringing it to a single point. They are used in reflecting telescopes because you're trying to gather as much dim light as possible. Light rays would leave the mirror as parallel rays. Concave mirrors are also found in flashlights, car headlights. Again, it's because the light is being brought to one single point. So concave mirrors, they are able to direct most of the light rays out in front. So for example, I'm in a flashlight or car headlights, right, exactly where you need them. All right, so here in dentistry as well, concave mirrors are used because it curves inward, and they are used in dentistry. Just some more uses of concave mirrors. For flashlights, they produce a parallel beam. In telescopes, they're able to collect a large amount of light from a distant source and focus it for viewing. In cosmetic mirrors, to produce an enlarged image. In the headlights of a car, they produce like a parallel beam again of light, and it can be directed down, which is a low beam, or straight ahead, which is a high beam. All right, just looking at the two different diagrams here of concave versus convex. So here we have the concave mirror, and notice what's happening to the reflected light, right? So it comes inwards, and they reflect parallel rays of light back through the focal point right here. And then when we see a convex mirror, they're reflecting parallel rays of light as if they came from a focal point behind the mirror. And then you can see it's kind of dispersing. All right, I'm going to pause here. 1 second. So next is rough surfaces. So we kind of looked at this at the beginning when we were comparing the two images. So here again we have like a plane mirror. It would be a smooth, flat reflecting surface compared to a rough surface. I think we were looking at a piece of paper, and if you close up to a piece of paper, it has this rough surface. So what you will see when you make these like ray diagrams is that smooth surfaces, they reflect light very uniformly. All right, so you see the normal, you see the incident ray, and you see the reflected ray, right? So if you look at the incident ray, and incident ray, they're all like parallel. Rough surfaces, they reflect rays at different angles, right? The reflected rays, they do not remain parallel. So if you look at the reflected rays here, here's a reflected ray, this one, and they're all parallel to each other. But what we see here is the incoming incident rays, they are still parallel, but the reflected rays are not parallel, all right? They're gonna bounce off differently, so the light becomes scattered. All right, but keep in mind that there is still the normal. There's still the normal and still the normal, and the angle of incidence will still equal the angle of reflection. All right, just looking here, a rough surface that reflects all light that strikes it will appear white, and a rough surface covered with ink, shown here in the middle here, will absorb the light. And since it reflects no light, it will appear black. All right, using reflections. So lots of uses. Cars and bicycles, they have reflectors to make vehicles visible at night. There's hundreds of tiny flat reflecting surfaces that are arranged at 90 degrees to one another. So then when light hits the reflector, the light will bounce off all of those tiny surfaces back towards the source of the light. Here, another use of reflections is playing pool, right? Like a light ray, a pool ball will travel in a straight line until it strikes something. All right, so here you have your cue ball and your target ball, and you can see like the image of the target ball here. So you're kind of aiming at this point, and so that the ball will bounce off and hit the target ball there. All right, so I'm just going to pause here and we'll watch these videos.